Saxon Advanced Math Lesson 20 is introducing our special triangles. Now, some of you may recognize special triangles from before, but we're going to go a little more in depth and explain where the special triangles came from and why they're so useful. Now, there's an infinite number of triangles out there, especially an infinite number of right triangles. But often in real life, we deal with two special triangles that come up over and over, and we're going to memorize those ratios of those triangles because we use them so often in real life, and allows us to work with trig functions without just putting them in our calculator and getting a random answer that we don't understand. We're actually able to see this work in real life by understanding these two special triangles. So the very first special triangle is a triangle. It's a 45, 45, 90, and we're going to look at how that came about. So if I just had a square that was 1, 1, 1, 1, very simple square. Well, because it's a 1, 1, 1, 1, if I put a diagonal across it, I would have two triangles that would be formed. Those two triangles that are formed, this angle has to be the same as this because these two sides are the same as well. If I want to think about it, this is a parallel line and this is a parallel line. That means this one has to be the same as this one. And since these are 1, 1, then alternate interiors have to also equal on these parallel lines on the transversal. So these are going to be 45, 45, 45, 45, 90, 90. Now, if I just took that triangle on its face, I would need to be able to find out what that diagonal length is. Because it's a right triangle, it falls into the Pythagorean theorem, a squared plus b squared equals c squared. So I put that in as my bases. Here they are, a squared plus b squared equals c squared. And I went ahead D for diagonal here. So 1 squared plus 1 squared. Well, 1 squared is 1, plus 1 squared is 1, and 1 plus 1 is 2. So there I say 2 equals the diameter of this squared, but I need to get d by itself, so I take the root of both sides and I end up with d equals root 2. So, and I went ahead and reoriented this so that we could see it. It's a 1, 1, root 2 triangle. There's my 45, 45, and 90. Now, let's move to the other one, and then we'll work some problems with this. And this one is going to be, if I took an isosceles triangle, equilateral, equal angular, and everything's the same, right? 60, 60, 60. And I said, well, let me find a height. Let me drop an altitude in there. So I draw a line right down the middle. Well, if I draw it right down the middle, it's going to be, this one is going to be 30, and this side's going to be 30. And since it is a perpendicular bisector to this, I end up with a 90-degree angle there. At this point, I can realize that this right here is just, if I did this triangle as 2, 2, 2, 2, and you'll see in a minute why I use 2's instead of 1's. Because I want half of something, and I don't want to work in decimals, half of 2 is an easy number. So that makes this a 1 and this a 1. So I have a 1 and a 2 on this triangle. The only unknown value is my height. So once again, I'm going to use Pythagorean theorem. However, I realize that I have a side length is unknown on this one instead of the hypotenuse, as in the last one. So I'm going to say this is 2 squared. There's my c squared equals a squared, which is 1, and b squared, which is unknown, which I'm going to put h for height in here. When I do so, I say 4 equals 1, that's 2 squared, equals 1 plus h squared. Subtract 1 from both sides, I get 3 equals h squared. Take the root of that and get the root of 3 equals h. So if height is root 3, I now have a 1, 2, root 3 triangle, and I'm going to go ahead and put that in here right on this side, on root 3. Now, a couple of things that I'm going to give you to help you remember this. This 1, 1, root 2 is really simple because you know two of the same sides, or two of the sides are the same. So it's always going to be 1, 1, and obviously root 2 is longer than 1. That's got to be the hypotenuse. And it's really easy to label it out. If I drew a 30, 60, 90 triangle, though, the problem we run into, and let me do a little better job of that, the problem we run into when we start drawing these 30, 60, 90 triangles is we get confused on which one goes where. So I still don't like that. Let's see if we can get this right on if I square up to it correctly. All right, so there I have my 30, 60, 90, and I look at it and I say, you know what, I'm going to label this one as my 30. And how did I know that? Because this is smaller than this one, and this was just a sketch. Keep in mind, my sketches are not going to be very perfect. So if you took and actually measured this, it's probably not actually 60 degrees. But we know that this is going to be a 90, and those do add up to my total, which is 180 degrees. Now I take my 1, 2, root 3 sides lengths, and how do I place them? Well, I think we can use a little bit of deduction here, that I realize that the hypotenuse has to be the longest side. 1, 2, and root 3. Well, we know that 1 has got to be the smallest. And a lot of students will get confused here and they'll say 2 and root 3. I don't really know what root 3 is, so it might be bigger because it's a bigger number. But here's how I know it's not. If I said 1 squared, that's just 1. 2 squared is 4. Uh-oh. 3 squared is 9. So the root of 3 is between 1 and 2. So root of 3 is between 1 and 2. Okay, so that means that this is not the longest side. This one here is. Well, if the longest side is 2, I'm going to go ahead and put that as my hypotenuse of 2. Now I look at this and I say I have a 60 and a 30. Well, the Hinge Theorem that you may remember from a previous lesson says that the bigger the angle is, the longer the side, the opposite, has to be if the two sides are the same. But one of them is locked in place. It's the hypotenuse. So I know that's not changing in length. So I look at it and say, well, obviously, therefore, the longest side, the second longest side has to be like second longest angle, or biggest angle, and the smallest, well, let's pick off the smallest. There's my 30, and I'm going to go ahead and play this a 1 across from my 30, because that's my smallest angle, and that's my smallest. Well, by deduction, the only thing that can be left is the root 3. So the root 3 is halfway in between 1 and 2, and halfway in between 30 and 90 degrees, 60 degrees. So this is a way to remember where those are. Now, let's go ahead and shift gears and look at a real example problem, 20.1. And they ask, what's the tangent of 30? Now, I realize that all of you have calculators at your disposal, and it'd be really easy to just plug that in the calculator and you get an answer. Now, we're going to know as a teacher, I'm going to know that you did that because you're going to end up with, most of the time, a decimal answer instead of a simplified radical. So, using the special triangle allows me to come up with a real answer that's very, very perfect. It's not rounded like a decimal would have to be rounded and cut off. So I'm going to look at tangent and realize that tangent of theta is opposite over adjacent. If you don't have those memorized, your sine, cosine, and tangent, you need to go back and memorize each one of those to be able to be successful with using special triangles and trig functions. So the tangent is opposite over adjacent. Well, what is the opposite over adjacent? Well, I'm going to my 30-degree angle, so I jump down to my 30 and I look for an opposite. Well, opposite to 30 is 1. Adjacent is root 3, so I plug that in. Tangent of 30 is 1 over root 3. And it's really that easy. The next step, though, and this is maybe not as visible to a lot of people, is that I never leave a root in the denominator. It's not very proper. So how do I get that root out of the denominator? And I don't need to use a conjugate. I don't need anything fancy because there's no addition and subtraction. I just multiply by the root of 3 over the root of 3, which is a fancy version of 1. That's why I'm allowed to do this. So when I do so, I say 1 times root 3, which is root 3. Root of 3 times the root of 3 is the root of 9, which is 3. And there I have the tangent of 30 is root 3 over 3. It's really that easy as long as you have these special triangles memorized. Look at 20.2. And let me go back before I do that and say this. You'll get to the point, if you do these enough, that you'll be able to see these triangles in your head and you'll be able to remember that what the sine of 60 is and the sine of 30. But until that becomes second nature for you, don't feel bad that you have to write these two special triangles out each time. It only takes a second. Sketch it on the side of your paper, wherever you need to do it when you're taking a test, because you're going to use these special triangles so much, you want to have them at your fingertips. Okay, so the next thing I'm going to do is 20.2, which is 7 sine of 45. Is the example. Now I'm going to break this down. I know that 7 is not shown all the way till the end. I'm just pretending it's not there because I need to find the sine of 45 before I could substitute in what that number is. So what is sine? Sine is opposite over hypotenuse. So I'm going to go over to my special triangle, and this one is confusing to some people, but you'll be fine. I have two different 45s. Which one do I pick? It makes no difference. So I can pick either one, and I say sine of 45. So sine, so I pick this one down here, and I say sine is opposite over hypotenuse. Now if I pick this one, that would be opposite over hypotenuse. Well, the opposites to each one of these are the same number, which is why it works that way. It doesn't make a difference which one I use. So sine of 45, opposite over hypotenuse. And when I do so, I say opposite over hypotenuse, 1 over root 2. I didn't take the time to write the step in there, but I multiplied the top and the bottom of this by root 2 over root 2 and ended up with root 2 over 2. Now that I have what that is, I'm going to plug in that root 2 over 2 with the 7 out front. Well, if I know the sine of 45 is root 2 over 2, I'm going to multiply it by 7. 7 root 2 over 2. And that's my answer. And these are not very difficult to work with as long as you'll take the time to memorize these two special triangles. 1, 1 root 2 and 1, 2 root 3 for 45, 45, 90 and 30, 60, 90 degree triangles.